Hi, this is Ari Everett for CSC120 in the fall of 2023. This is my conversation piece 3 for the sequential circuit module. chose a 4-bit asynchronous gray code converter with multiple display outputs and binary converter. Specifically, those multiple displays are the 4-bit gray code itself. I have a gray code to binary converter that has a 4-bit binary output as well as a single digit hexadecimal 7 segment display. This will be the page. This video is a placeholder for this video that I'm recording right now, so you can disregard that. My goals in this were to create a device that was applicable to the real world and also get through a complex sequential circuit I made on my own. This module was very challenging for me, especially steps 3, 4, and 5 in the design process, next state table, Boolean equations, and building the circuit out. So I set out to do that, and I'm proud of what I created here. I went through the design process. I utilized both the engineering design process that we learned in FSC 100 and that is used in the industry across engineers, and the 5-step finite state machine design algorithm with these steps outlined here. I started off with some brainstorming here for the Merely and More circuits, various topics, concepts, and devices that we had built. Ultimately, I came up with 2 good ideas and with the gray code idea. The other idea was a stoplight in the middle of nowhere on a constant timer. I thought that would be very applicable and expandable to what we did in class. But I chose the gray code because I thought this was even more full circle, because I created a gray code converter in conversation piece 1, and I could attach that and expand that here to make it even bigger of a circuit and build out. Here are my steps. 1, state diagram. I'm proud of this. I think it's the biggest state diagram that I've done with 16 different state codes. Here's a decimal to binary to gray code table that I pulled off of Google. Arbitrarily, I chose the JK flip-flop. Here's my next state table that I built in a spreadsheet with some personal markers with red and circles to make sure I lined up everything correctly when creating this. This was a very cumbersome piece of the build-out. This was another very cumbersome piece of the build-out, the Boolean equations, looking back at the next state table and building this out, creating the equations in the green rectangles here, and then simplifying with the Boolean logic laws. And then finally, we have implementation. Pictures of design here while it's running on the right. I'll be back to the demo on the right as it runs and finish my explanation here. And then reflection and files at the bottom here for the full write-up and white paper. So on to the build out in step 5 after you create the Boolean equations. Overall, I'm very happy with the build out here. I'd like to note that it's very important for designers and engineers to have good way wording and interface, and that's what I focused on here. From a low level, even wire management is well kept. High level, the sections and sectors are each labeled correctly and as easy to read as possible, top down, left to right, or circle method that humans are used to. So let's go through this circuit here. The clock is running at a certain frequency. These clock sets and reset here were just pass-fail checks to make sure that the tunnels were working. Next, the state memory is built out with the 4 JK flip-flops. There are various inputs and outputs. Next state logic is what is going through those logics, those flip-flops, to create the custom counter that we wanted. On up here to the output, which is the subsections of that are the 4-bit gray code. From most significant to least significant as you read it left to right. The LEDs are merely are just user interface because I thought that these pins were rather small, so this was much easier to indicate a higher or lower to the user. Here's the gray to binary converter I created 4-bit decimal here on the right, most significant to least significant as you read it, along with the LEDs. I cannot take credit for this device here. This came with the library. This was the 4-bit DESI to 7-segment display that shows it in 1-digit hexadecimal. So you can see here it goes through the 16 count, 0 to 16, or 0 to F in hexadecimal. Some conclusions, highlights, lowlights, and ideas here is you can see the logic here is unsimplified in flip-flop 1 and 0. I had a very frustrating and proved very difficult problem for me. You can see on the left here I did simplify them, but once building out it was a different story. So I went through different iterations, several hours of added work to try and troubleshoot, but was unable to get that. So I would love some insight from someone to see how this could be built out. Real world problems, this could create longer propagation delays, be more expensive with the more chips. However, these may be negligible in the real world as well, and at least we know that the circuit works here and the logic is a lot easier to follow other than the XNOR or XOR. I'll show you the other build outs that I had. This was the initial one with the simplified logic you can see, but unfortunately with this, the count only got to 1, 1, 1, 1 and stopped there. You'll see that in a second. There it is. So I tried many different combinations. We were working all the way back to the state diagram, troubleshooting different methods to try and get the circuit to work, but unable to. Here is the gray to binary converter I created from the research I did in Conversation Piece 1. It is the XOR method of doing it, or what they call the reflexive or mirrored method to creating gray to binary conversions. Finally, some other ideas to expand or for next time on this. One thing we could do is add another 7-segment display here to make a true 2-digit decimal output, which humans are much more accustomed to, counting in decimal. So seeing a 2-digit decimal display here from 0 to 15, I think would be really, really great. Another thing we could do is set a switch to count up or down. That would add a 5th flip-flop and 5th more logic, and also the elusive 5-input K-map to build out, which would be a fun exercise to go to. Otherwise, overall, I'm very proud of this circuit and this project here. It was a difficult module for me, and this is the most complex circuit that I have built. So I'm proud to have gone through the design process and created something successfully, with some caveats to some fallbacks and ideas for next time. But otherwise, I think it's a very well designed circuit with real world applications. And that's it. Thank you.